I want to talk about the Bekenstein entropy and the Hawking temperature. Both of these expressions are in error. The entropy that comes out is a convex function and not a concave function, as must be by the second law. First, I'll do a small derivation of the Bekenstein entropy, and then we'll discuss it in more detail. If I want to fix a dimension, which they call a thermal wavelength, that is, it's a characteristic dimension which depends upon the temperature. What we have are h bar times c is energy times distance. So if we divide that by an energy, we will come out with a wavelength. So if I divide that by the thermal energy, say, this we can say is a thermal wavelength, and since it has c incorporated, this would be the relativistic thermal wavelength. Okay? And from this, now, what we do, the only thing we know about a black hole, charge, whatever you want to talk about, hypothetical, we know that its radius, and that is given by the Schwarzschild radius, c squared. And from this, we can get the temperature. And the temperature comes out to be K is Boltzmann's constant. E, PL is the Planck energy, which is enormous. H, C to the 5th over G, which is 10 to the 19th. A very high number. Okay? So, in this context, Hawking claims that tiny black holes will radiate energy away from the black hole and eventually will evaporate. Okay? The spectrum at which it evaporates is a black body spectrum. Black body spectrums don't evaporate. There's an equilibrium between the cavity in which the black body is and the photons which are inside the black body. So photons are absorbed and readmitted using a piece of charcoal. They go from infrared to ultraviolet. There are no bursts of X-rays involved. So, in fact, black body radiation can be viewed as a phase equilibrium, where H is the enthalpy density, P is the pressure, and this is the famous Clapeyron equation. And it says that if the black hole satisfies an equation like this, or black body in this case, there are two phases are the phase in which there are photons and the phase in which there are not photons. So this is the black body radiation. The number of intensive parameters is F. R minus M plus 2 is the Gibbs phase rule. The number of components is 1. The number of phases is 2. So the number of intensive parameters is 1 in this case. And P can vary independently of the volume. So the volume can be adjusted to maintain this phase equilibrium. That is, if 1 mole of substance passes from one phase to the other, the volume will change accordingly. Okay? And there is no evaporation in this mechanism. It's an equilibrium established between the two phases. It just so happens that for black body radiation, the chemical potential vanishes. Okay? So, if T is a temperature, we can use the second law and obtain, the second law says that ds in dE is equal to 1 over T, the temperature. And we know that the temperature, the inverse temperature is given by K 2E over E squared. And we can integrate this immediately and obtain the entropy plus a constant, arbitrary constant of integration. Okay? The first thing to notice is that the entropy is a convex function of internal energy. Which is not entropy. Okay? The entropies that we know, or the second law provides, are entropies which are concave. The slope of the entropy versus energy is 1 over the temperature. And as the temperature becomes infinite, it reaches a plateau. Here, 1 over T continues to rise. It's not the second law. Now, this is more or less the derivation that Planck did. Planck started from the expression of 1 over T, which he got from Wien's law, integrated it, and he found the Poisson distribution for S. Then he differentiated this again to look at the fluctuations involved. And the fluctuations are given by the negative of this, which is 1 over T squared dt in dE, which is equal to minus 1 over T squared C, the heat capacity. Okay? So from this we can write down the heat capacity as C is equal to minus E Planck squared over 2kT squared. It's negative. But people say there's nothing to worry about. Black holes don't pertain to our universe, our world, and therefore in the universe you can find black holes or stars which have negative heat capacities. Nothing to worry about. But such a beast will never come into equilibrium with anything, much less show a spectrum of black body radiation, which in its equilibrium is a necessity, which is obtained from this equation. So, the first question we have to answer, can heat capacities be negative? So, during the 1800s, people were looking at convective equilibria. Lord Kelvin was looking at it in respect to the thermal and convective currents underneath the Earth's surface. And polytropes are certain types of materials which satisfy an equation of this order, where N is a constant, P is the pressure, V is the volume. You will notice immediately that temperature is lacking from the system. So polytropes are very special objects. This is more or less like an adiabatic constraint. So if during the process of stirring, a quantity of heat is given to the system, it will be proportional to the change in temperature, and the constant will be C. Notice that I'm using an empirical temperature, not necessarily the absolute temperature. The empirical temperature is a monotonically increasing function of the absolute temperature and vice versa. So if C is 0, we have an adiabatic system. If C is infinite, we have a isothermal system. And if C is negative, they say that we should have a negative heat capacity. So let us consider an ideal gas as an object that we can work on. The equation of state of an ideal gas is equal to A. A is a constant, it's the gas constant. And we can write that as the difference of the heat capacity at constant pressure minus the heat capacity at constant volume. Okay? And then we can use the doctrine of latent and specific heat, which says that the change in the heat is due to the insensitive heat, LV in dV plus CV in dt, T empirical. So we have two independent variables, volume and temperature, and L is the latent heat, and C is the heat capacity. So we want to introduce this into this equation, and if we do so, we come out with dt over t plus n minus 1 dv over v is equal to 0. Now we use the fact that for an ideal gas, LV is equal to P, the hydrostatic pressure. An ideal gas is a very particular case in which, from the first law, LV is equal to P. It doesn't depend upon volume, it only depends upon temperature. So we can solve this equation now for n, and we find n is equal to Cp minus C, Cv minus C. We introduce the equation state of an ideal gas. Thus, we have dq is equal to, at the end of it all, once we apply the constraints, Cv minus A n minus 1 times dt. Okay? And the claim is that in the interval for n less than gamma, which is the ratio of Cp over Cv, this C can become negative. Even if this were the case, that C has nothing to do with the heat capacity as we know it. Doesn't come anything to do with the second law. And the second thing is that the temperature and volume are no longer independent, but are rather related by the adiabatic equation, which is what we use to derive this, which is V n minus 1. T is equal to a constant. So it is neither general, but it's a very demanding thing. So we can analyze this term here by relating it to a thermal equation state, which is called the Gruneisen equation state, known from the late 1800s. And the Gruneisen equation of state says that the ratio of the compressional work to the internal energy is a parameter, S. Okay? S can vary from a relativistic gas of 1/3 to a non-relativistic material ideal gas of 2/3. Okay? That's the range in which it goes. And for an ideal gas, this is equal to gamma minus 1, the ratio of the specific heats minus 1. This is 5 amps, and this is 3 amps. So we have the ratio of the specific heats. So introducing this into the first law, we get dq is equal to dE plus P dV, and we can relate P dV, putting in the Gruneisen equation, and we have dE plus SE over V in dV. Okay? So now we know that dq is not a conserved quantity, but there are an infinite number of integrating constants, which can be used. One such integrating constant is multiplying this by Vs, both sides. And in doing so, we come out with d e to the Vs. So that t, where we have the other relationship between v and t, this comes out to be t Vs is equal to a constant. Okay? Now recall that we have s is equal to n minus 1 for n greater than 1. Thus, we come out with the fact that n is equal to gamma. If n is equal to gamma, here we have Cp minus Cv minus Cp minus Cv, all multiplied by dt, and that is equal to 0. Thus, for an ideal gas, C can never be negative. I repeat, even if it could be negative, it has nothing to do with the second law. The second law outlaws such types of behavior. But even here, for an ideal gas, it vanishes. Now, I think the most convincing proof is to show that the relationship between temperature and energy is not monotonic, but inverse proportional to one another. The hotter the system, the more internal energy there is, the cooler the temperature, which makes no sense whatsoever, and also leads to unacceptable conclusions. What to talk about now is the unevenly heated black hole. Okay? What is an unevenly heated black hole? As far back as 1852, Kelvin, in his thermodynamic studies, wanted to obtain a criteria for equilibrium. So he took a body, divided it into many cells, with adiabatic walls between them, so that they could not communicate, they cannot transfer heat from one to the other. And each of these bodies were set at different temperatures, T1, T2, etc. And then, by replacing the adiabatic walls by diathermal walls, he wanted to study how the system came to equilibrium. Okay? If the walls were removed and there was no ideal engines inside, that is, ideal steam engines, could do work inside these cells, no work would be done, and the equilibrium temperature would just be the arithmetic mean temperature. Okay? But if I had little steam engines, ideal engines, in each of these that could do the maximum amount of work, Kelvin obtained the conclusion that the mean temperature of the final resting state of this object was the geometric mean. We know that the arithmetic mean is greater than the geometric mean. Lower temperature means more work is done, according to Carnot. So in this context, we can look at the first and second laws, apply to a black hole, and see what the mean temperature, what the black hole mean temperature predicts on the basis of this inverse relationship. So the first law says that the change in energy over a cycle should be 0. Now, each of these cells are characterized by their masses, m, j, multiplied by a constant, which would be a heat capacity of the system. So the internal energy would be the heat capacity times the temperature. So if I have all these cells, first it's negative here, because of the sum of the mi. We want to integrate from all the initial temperatures, Ti, to a common final temperature, Tf, of dT I over Ti squared. This comes from the fact that the heat capacity, integrating this, the final temperature, this would be 1 over T, the total mass, which is the sum of its masses, divided by the final temperature, T, minus the sum of Mi, Ti. And this should be equal to 0, conservation of internal energy. So what the black hole does at this point is to select out the harmonic mean, okay? The harmonic mean is lower than geometric mean. So according to Kelvin, we've done Kelvin in. We can get a temperature even lower than his geometric mean temperature, which would be the lowest one possible. But wait. We have to be careful that the temperature doesn't go to 0, because they become infinite at that point. So we have to exclude absolute 0 from this. But people say that there's no problem, we just keep the system away from absolute 0 and it's perfect. Okay? So this harmonic mean, 1 over T, is equal to 1 over M times the sum of Mi, Ti. Okay? Now, apart from the fact that this would, like I said, violate the third law, which in its strong form would read, the limit as the temperature tends to 0, the entropy goes to 0. And this does not happen. So we violated the third law. We've also violated the first law, the 0 law, because taking two systems in equilibrium, they must reach a final common temperature. Since the temperature is inversely proportional to the energy, this will never happen. So we violated 2 of the laws so far, and also the second law to boot. So we have a violation of everything. Now, rather than looking at n systems, we can look at 2 systems to make it more simple than looking at n systems. For 2 systems, we have that the final temperature is equal to M over T final times C, this constant, which is equal to Cn1 over T1 plus Cn2 over T2. And this is just the sum of the energy of the first subsystem and the second subsystem. Okay? Well, nothing particularly exciting about this. Now we want to look at the second law and what that says. The second law says that delta S must increase. So M over Tf squared, we divide by 1 over T to get the second law, minus M1 over T1 squared plus M2 over T2 squared. And that must be greater than 0. Okay? So, at this point, I can transfer to energies, and if it was the same type of behavior, monotonically increasing, then there would be no problem. But wait and watch what happens now. This is equal to E final squared over M, and this must be greater than E1 squared over M plus E2 squared over M, where I just used the definitions of energy. And I can make another simplification, that M1 is equal to M2, and the sum is equal to M. And if I do this, I get E1 squared plus E2 squared is greater than 2 E1 squared plus E2 squared. And multiplying this out, we obtain 2E1 E2 is greater than E1 squared plus E2 squared. And this is impossible, because E1 squared, E1 minus E2 squared, perfect square, and it must be greater than or equal to 0. So this is wrong. And so is the expression for the Hawking temperature is wrong. So we've used the property that the means are monotonically increasing functions of their order, that the arithmetic mean is greater than the geometric mean, is greater than the harmonic mean. This is the case where no work is done, this is the case where maximum work is done, and this is the case which is completely outlawed, harmonic mean. Because energy is not an increasing function of the temperature. So therefore, we've shown that what quantum gravity admits to as an example, that is that quantum gravity should satisfy black hole thermodynamics, is completely wrong. Okay?